In this video, we will compute the line integral of a vector field. So the first thing I want to point out here is that there are several different notations for line integrals of vector fields, and they all mean the same thing. So before we get started, I should just point out that although in this video we're using this notation, there are two other common notations which mean the same thing. One other notation, which is sort of the definition of the line integral for a vector field, is to say f dot the unit tangent vector and then ds. So we borrow the notation for line integrals of scalar functions. And this means the same thing. And yet another notation is to write it like this. Write the x component, which in this case is x squared, dx, plus the y component, which is negative y in this case, dy. And this again means the same thing. But I sort of prefer this first notation, so I'll stick to that in this video. Okay. So, just as we did for the line integrals of scalar functions, the first thing we want to do is get a parameterization for the curve, since it wasn't given to us. So what does the curve C look like? Well, it's described as a piece of the parabola x equals y squared. So here's the parabola x equals y squared. And it says it's the part that goes from 1 minus 1 to 4 comma 2. Oops. So it's this part of the curve that goes like this. Okay, so let's parameterize this. Since the curve is a graph, this is very easy. Here y is the independent variable, so we can just have the y part of the parameterization be t. And then the x component is given by the equation for the curve, x equals y squared, so we just put t squared. And it's as simple as that. And so in this case, t will go from minus 1 to 2. And we'll need the derivative in order to compute this. So let's do it now. This will be 2t comma 1. Okay. And just so we remember, let's label these components of R as x of t and y of t, just as we did in the other video for the line integrals of scalar functions. So let's see. So to turn this into an integral that we can do, we're going to substitute everything in terms of t. So the bounds of the integral will just be given here by the bounds of our parameterization r of t. So it will go from -1 to 2. And then we just write f. F is x squared comma minus y. But we need to substitute for t, so we use x of t and y of t from the parameterization. So for x, remember x was t squared, and we have x squared, so we need to still square that, comma minus y. And from our parameterization, y was just t. Dot, and for dr, we simply use r prime. So dot 2t comma 1, and then dt. So now once we do this dot product, it will be like an integral from Calc 1 in just one variable. So -1 to 2, and let's do the dot product. So t squared squared, that's t to the 4th, times 2t. So that's 2t to the 5th power, plus minus t times 1, so minus t. And now this is a very easy integral. So this is just t to the 6th over 3 minus t squared over 2, evaluated from -1 to 2. And if we plug this in and do the subtraction, we'll get 117 over 6, which can be reduced to 39 over 2.